Hey everyone, and thank you for giving me this great opportunity to present my paper on behalf of me and my supervisor at Chalmers University of Technology in Sweden. I'm Hassan al-Karawi, a third-year PhD student at the same university. My research was partially financed by the Swedish Traffic Authority, Trafikverket, and partially by Swedish innovation agency, Vinnova. The paper carries the title, Fatigue Life Extension of Welded Steel Structures by High Frequency Mechanical Impact Treatment, or HFMI treatment in short. So the presentation will be divided into four parts. First, we will give a general background on fatigue in steel structures and why do we tend to use HFMI treatment, what is the function of this method and what potential does it have. Also presenting the methodology of the paper, presenting some results and findings, and finally draw some firm conclusions. To start with, why do we care about fatigue in welded structures? Whether it's for bridges, whether it's railway or road bridges, once we are doing welding, we have different, of course, positions to weld, whether it's transverse attachment, butt weld, cover plates, rat hole, and so on. We always create three different negative effects. So first, we put a lot of thermal expansion and contraction in a specific location, which causes tensile welding residual stress to take place at the weld toe. Also because of the abrupt change in the stiffness. Specifically at the weld toe, this causes stress magnification or localization at the weld toe, which magnify the level of stresses here. Also because of the extreme heat that we're putting in the structure locally, we got usually some defects, and one of these defects exists in the same position at the weld toe. This, of course, aggravates the fatigue problem, and all of these factors causes a crack initiation, which develops to propagate through the plate thickness and finally causes fracture. That's why for fatigue-prone structures, we design the structure for specific fatigue life, of course, depending on the functionality of the structure, also the plate thickness and other factors, and so on. As we mentioned before, we have tensile welding residual stress and sharp weld toe. These are the negative impacts of welding. You can use this small machine, which weighs less than 1 kilogram. It's easy to maintain, easy to operate, and of course, easy to handle. Any labor can use it. And it requires very short time of training. And you're peening your structures with a very high frequency and creating this plastic deformation. This introduced compressive residual stress at the weld toe, which counteracts the effect of bad tensile welding residual stress. And it also reduces the sharpness of the weld toe with this small nice groove. Well, this method is not new. It has been in research for more than 20 years, and it has also been introduced in several standards and recommendations, such as the IIW recommendations, International Institute of Welding, and also AASHTO, and it also soon will find in its position in the Eurocode draft, hopefully. But most of the research is on new structures and not existing structures. Well, for existing structures, they have accumulated some damage and probably they contain some fatigue cracks. So we still have a lack of knowledge on these kind of structures. And this is the topic of my paper. So the aim of my paper is to quantify the degree of improvement in fatigue life via HFMI treatment, specifically for in-service structures, which probably contain crack. So how I did that, it's a simple literature study. I've collected more than 130 fatigue test results from several research papers. And we analyzed them together. So the study also includes different type of details, which is of interest for bridge engineers, such as transverse attachment, longitudinal attachment, butt welds, and cover plate attachments. Finally, we use something called, we call it the gain factor in fatigue life, which is a ratio between the fatigue life obtained experimentally for cracked or in-service structures obtained in the lab, divided by the design fatigue life according to the IIW standards and recommendations. And I use this standards in specific because they provide some guidelines how to quantify the degree of improvement theoretically for different types of details. Here in the figure, you have the description of the studied data pool in terms of the stress ratio, in terms of the studied steel strength, and also the availability of the crack size in the research paper. So you can see that more than half or 50% of the data points contain or there is a description on fatigue crack size, while we have also some papers which does not describe the fatigue crack size. So that requires, of course, different kind of analyzing or studying. Yes, and this is the expression of the gain factor. We will see this expression a lot in my presentation. In extension of the cracked structures divided by the design life. Yes, so to start with, for the crack size effect, on x-axis, so we plot this. On x-axis, you have the crack size described in the paper, and on y-axis, you have the gain factor, which gives the ratio between the nx divided by niiw. What we need to find, it's the gain factor. If it's greater than 1, that means that we can, or HFMI treatment has the potential of improving the fatigue life even when the structure contains crack. And this is what we found, that we got always the gain factor to be greater than 1 for almost all the data pool. It was mentioning that only the data points which contain fatigue crack is included here in the figure. So this is much less than 130 data points, but for all of them, the gain factor is greater than 1. Well, there's no much data points for crack size deeper than 2.25 millimeter. So we can limit our conclusion here so that we can use HFMI treatment to treat cracks and give good fatigue life extension even when the crack reaches 2.25 millimeter. Also, another observation, it's a side observation, that when the crack is created artificially, the gain factor is much higher. And this is, of course, understandable because this kind of crack, the artificial crack which created by machining, lacks a plastic zone area, which gives, of course, very conservative results. So this is not the best way for presenting fatigue crack. Authentic fatigue crack can be created by fatigue testing. That's much better. As I mentioned, almost 50% of the data pool contain, there's no description on fatigue crack size. So that requires another way of analyzing it. And this is what we do. This is what you will see in the next, the coming slides. But here we need to understand why do we get high gain factor. Here is a figure from another publication, which shows that when the crack size increases, the area or the plastic zone area introduced by HFMI treatment decreases. But for crack size less than 2 millimeter, we can get plastic or compressive plastic zone area around the crack tip, which is very favorable and good for arresting the crack. So that gives us an understanding why do we get good fatigue life extension. And here we can say that it's related to 2 reasons. First, because the studied fatigue cracks are shallow. All of them almost are less than 2.25 millimeters or 2 millimeters. Also, the introduced compressive residual stresses, which for this kind of cracks, which arrest the crack propagation. Here in the study, we have that when the crack size is less than 1.5 millimeter, we can get good compressive residual stress to arrest the crack and cause it not to propagate anymore. So here we include more data points, but now the x-axis is different. Now we don't have the crack size anymore, but we have the ratio between the number of cycles, which is the structures has tested to before repair or before fatigue crack repair using HFMI treatment, divided by the experimental fatigue life of the as-welded detail. We can say that when this ratio reaches 1, that means that the as-welded or the experimental as-welded life has been reached. And this is what we see, that the gain factor is always greater than 1, even when this ratio reaches 1, which is very promising, that we can get fatigue life extension even when the structure reaches its real fatigue life. That's very promising. But in some papers, we don't have a description on what is the experimental fatigue life. So instead, we use the design fatigue life according to the IIW. And I would say that this is the best presentation of the results, because this is what the designer used. The designer used the described value according to the Eurocode or the IIW. And this is how she or he determines the fatigue life. So we want to see if the design fatigue life is reached. Can we still rely on HFMI treatment in extending the fatigue life? This is what the figure tells us, that yes, we can. In almost in all the studied data points, the gain factor is greater than 1. So regardless, so we can say that regardless to how much the structure is re-fatigued to, we can just only look at the structure. If it contains a crack deeper than, if it's not deeper than 2.25 millimeter, we can use HFMI treatment for treatment, so confidently, yes. But we got a lot of scatter and gain factor, as you saw in these 3 figures. And this is of course related to 2 different factors. One of these factors is the scatter or variability in the introduced surface residual stresses, as you can see here in the figure. So this on x-axis you have the ratio of the introduced residual compressive residual stress at the surface divided by the steel quality, and you can see that this ratio varies between 0.4 to almost 1.7. So that's a lot of scatter, which of course will be reflected on how much do we gain from HFMI treatment. But it's always good. I mean, it's only a matter of how good is it. Another factor is the difference in crack detection accuracy. In some papers, the crack size was quantified very precisely because the crack was created artificially. So we have it as a pre-knowledge how large the crack is. In another paper, we use some crack detection method like ultrasonic testing. In another papers, we use less accurate detection methods such as dye penetrant and so on. So that of course will be reflected on the gain factor. Here we come to the end of our presentation, and let's wrap up. First of all, we can say that HFMI treatment has the potential of increasing the fatigue life or causing fatigue life extension of in-service or existing structures, even when the structure contains a crack of 2 or 2.25 millimeter crack at the weld toe. Also, we can say that the gain factor, obtained gain factor, is always greater than 1, even when the structure is re-fatigued to the as-welded life or even longer. So it's a matter only on the crack size and not how large or how long the structure was pre-fatigued to. So the in-service fatigue life is not an issue. And finally, we can say that the scatter in the calculated gain factor is related to the variability in introduced residual stress and also the crack detection accuracy.